Hello everyone, welcome back. This video is going to be a brief video on the idea of statistical independence and what that means. In this video, we're going to start off talking about the difference between mutually exclusive versus independent. We're going to give some definitions, some formulas, and then end with a few examples. So let's start with this idea of mutually exclusive versus independent. Well, mutually exclusive is when things cannot happen at the same time. Sometimes we have Venn diagrams where we have one circle like this and the other circle not touching it, no intersection. Examples of this would be like if I took out all the face cards. So I have A's 2, 3, 4, 5, 6, 7, 8, 9, 10. And I try and draw a face card from that pile. It's mutually exclusive. It's not something that can happen at the same time. If I have a 6-sided die, I can't roll an 8. Now, independent is when one event occurring does not affect the other event. So knowing the second doesn't change what you know about the first. Now we're going to start with kind of the easier to understand definition, and it's knowing if the second event occurs does not affect the probability of the first event. Some examples of this are flipping a coin, rolling a dice, spinners, or problems with replacement. So if you have a problem and you have a bowl, and in the bowl you have yellow marbles and green marbles, and they're replaced, that's with replacement. And so you're drawing from the same pool. Now, the more mathematical definition is that event B is said to be independent of event A if the probability of B given A equals the probability of B. Something important to note here is that we're looking at the probability of B, and that is if we look at the conditional, it's the probability of that event happening given the condition. We can't say that the probability of B given A equals the probability of A. That's not independence, because our A is not, our A is the condition, not the event. So there's a few different ways that we have that we can prove this mathematically. The first, as we discussed on the last slide, is the probability of B given A equaling the probability of B. We can also use the special multiplication rule, because if these events are independent, they'll equal each other. So if the probability of A and B happening together equals the two probabilities combined or multiplied together, then you know that the events are independent. So if, for example, I tell you that probability of A happening is 0.22, and the probability of B happening is 0.1, and the probability of B and A together is 0.022. I would plug these in and see if they match. So I would say, is 0.022 equivalent to 0.22 times 0.1? And that's another way to show that they're equivalent. Now, they won't be equivalent if, for example, we say the probability of A happening is 0.34 and the probability of B happening is 0.2, and then the combined probability of B and A is 0.8. So we would then put everything in its proper place and say 0.8, is that equal to 0.34 times 0.2? And it happens that 0.8 is not equal to 0.34 times 0.2 because that equals 0.068. And this applies when there's more than one event as well. We would just put the probability combined and multiply by the probability of each happening. All right, so now let's do some examples. To start off, we're going to say is the conditional probability of S given A is 0.867, and we need to know if these events are independent. We're given that the probability of S is 0.5309. So then we say, okay, is the probability of S given A of 0.867, is that equal to 0.5309? And it is not. So these events are not independent. Now we have the probability of E happening is 0.72, and our conditional probability of E given G is 0.72. So we'll match the sides up according to our equation up front. So probability of E given G is 0.72, and the probability of E is 0.72. So we know that these are independent. Now let's look at the probability of C given H is 1/2, and the probability of H is 1/2. So let's look at the probability of C given H. We know that that's 1/2. But there's a problem here. Our H is our condition, not the event. We would need probability of C in this event. And because it's the probability, the event C given H, and we're only given the probability of H, there's no way that we can say for certain if these events are not, because we need the event, the probability of the event, and not the condition. So this, we're just going to put some question marks there. So for our last example is where we take the principle of the probability of B and Q equaling the probability of B times the probability of Q. And this is because we don't have the conditional, the probability of the conditional, but this is what we're given. The probability of B equals 0.08 and Q is 0.05. So, and combine it's 0.4. So does 0.4 equal 0.8 times 0.5? And the answer is yes, 0.4 is going to equal 0.4. And these are some ways that we can mathematically show the independence.